Let's pretend we're actually doing the observing tonight, which we're not, but we'll pretend we are by tomorrow. And let's now take a look at the couple of things here. If you remember, I showed that discovery paper. Notice the title of that paper, Kelt 1b. They're already sort of suggesting it's a exoplanet with the B. A strongly irradiated, highly inflated, short period, 27 Jupiter mass companion transiting a mid-F star. Okay, so we should probably dissect that, right? Strongly irradiated, close to the star, getting a lot of radiation from the star. Highly inflated, big. Short period, 1.2 days. 27 Jupiter mass companion. That's like huge. Unless I missed a decimal point there. That's like huge. Transiting a mid-F star. So an F star, middle of its life. So that's the paper. If you look through the paper, and I did it a couple of times, you will not find it saying it's an exoplanet. Yes? Yeah, it's what professional astronomers call big. No, I'm not kidding. I'm sorry.
Well, really, but I mean, there may be a distinction in some gradient across it or something.
Yeah, I haven't researched that. I'm sort of being joking here.
There actually is. There is a difference.
Bill.
There is a difference. A number of them that they discovered recently are called puffy because they have a density much, much less than Jupiter. So, and then there are big Jupiter-sized stars that have a similar density. So I think it's an issue of density.
So Bill's point about highly inflated, meaning a core, low density core with gaseous or whatever planet. Okay, the thing then that we would pick up from the discovery paper and from the NASA exoplanet site and the other sites are these key parameters: R star, B magnitude, the effective temperature, metallocity of the star, and the surface density. Again, these are the key things that would go on our spreadsheet that we then later use for input to AstroImageJ. We talked about the worksheet. Let me pass around the one specifically for Kelt 1 that I've already filled out. Bob, somebody I could get your help with? Pat, if I could get your help with on that side or whatever. There you go. So this is a worksheet I've already filled out of the observation I did October 12th that we'll be dissecting tomorrow. I'll wait till everybody gets a copy here. Okay. Everybody have a copy? Okay. All right. So let's walk through it. So what I've entered here is the right ascension and deck of it. I put in the period in days, and I think what I did here was to put in that updated period, or maybe in the original. I forget. We go back and look. R star, effective temperature, V magnitude 10.7, and as I said earlier, what pops out is the suggested range of comparison stars. Should be from 10.26 to 11.45. Okay, so that's the suggested. Now I will say that You know, I'm not strict myself on trying to stay within that range, but I try to, and it just helps with better post-analysis where you'll see that stars that are comp stars that are way off in magnitude kind of skew things, and you know you have to deselect them. So I do try to stay within that range. Date of the observation. The BJD, TDB, ingress and egress times. Now let me just go back to some of those predictions we talked about earlier and see where we got those. Okay, so let's see. Is this the right one? Six, 7, 4. Now this is tonight. This isn't going to show it. These were. This is. I apologize. This was October 12th. This is today, so that's why they're not the same. But the. I believe what I used here. Let me just check the period. So the period of. Yeah, I used closer to the NASA and ETD periods, and you'll see then why I was off by 30 minutes. So I used these close to these periods. I'm not sure why I put in 5007 versus 514, but nevertheless, I used closer to these two periods, which are off by, as we'll see, about 30 minutes. Okay, so back to the worksheet. So I put in ingress and egress times. It predicted a midpoint of what you see there. That model fit midpoint I put in later after the observation. So put that aside now because pretend we haven't done the observation. Latitude and longitude are my home base. I'm at sea level. Aperture 280 millimeters. Focal length, what you see. My camera with the gain, read noise, dark current, point of saturation, number of photosite size, binning, and so on. You notice I did 2x2 binning. The reason I did that is because the amount of the full width half maximum at my location, which if you go down and look at 29, line 29. Actually, the seeing wasn't too bad, 1.89 arc seconds. That represented 3.36 pixels on my CCD camera, which was good. And remember I said the guideline should be between 3 and 5 because we want to spread that light over that full width half maximum, which is the peak of that airy disk. We want to spread that over 3 to 5 pixels. So I've kind of in that good range there. So this then is the data I entered. Now the filter I used was a V filter, and when I went to that site I showed earlier, because it doesn't know about Kelt 1b, I plugged in the coefficients that I got from up above, the TF, say the effective temperature, velocity, surface gravity, plug those in, and I got those limb darkening coefficients you see there, 0.3486 and 0.315, etc. So that was all filled out ahead of time before I actually did the analysis. So we can kind of pretend we're kind of at that stage right now before we actually do the analysis. Question?
21, put number 21 there.
Yes.
How do you determine that?
So empirically, everyone should test the linearity of their CCD camera by doing the following. Start taking images with increasing exposure time, looking at the ADU counts, do a graph to see where that if you divide the ADU counts by the exposure time to get ADU per second, you'll see it go linear, and then you start seeing it drop off. So
Does it depend on the magnitude of the star, or is it going to be a simple?
now this is just to characterize your. You just pick a star and just to characterize the linearity of your CCD camera, just to see where it goes nonlinear. And that's the point. Actually, earlier than that is what you want to put as sort of the threshold. Okay.
Where did you identify the magnitude of the comp stars? What did you do for that? Do you have a field of view?
Yeah.
Software that you use?
Right. So the question is, I know I want to get comp stars in the range 10.26 to 11.45. So I look at my field of view, and I either go to Star Catalog, or if I actually plate solve and come up with the coordinates of those stars, I can go to Simbad, take a look at that. Some of the planets I use for the Hubble thing, I got AVSO to what's called sequence the field of view. Namely, they came up with good comp stars for us, so we knew what range they were in, so that made it easy. But if you're just generally doing any old exoplanet on your own, you're probably just going to have to do the best you can. Now, one of the things, a quick way of doing it, rather than having to go to a star catalog, as we'll see tomorrow, is when you put the aperture from AstroImageJ on it, it will show you at that time the ADU counts. And you can kind of see if they're the same as the target star, in which case you know you're kind of close in magnitude. So that's kind of what I do, actually, rather than go into the business of...
You had a way to be sure that you were picking the darkest star.
So the question is there a way to pick up if you know there's variable stars? No, not unless you go to a catalog. But you'll see it very obviously once you do the analysis. You'll see one of those comp stars doing a dip. Yeah. Okay, so any other questions? We're going to kind of segue from the worksheet then back to the presentation. But this is going to be key for tomorrow as we do the actual observation, because we're going to be entering some of this data into AstroImageJ to actually do the modeling. Any questions? Okay. Okay, so AstroImageJ. This is the download site. Now, Pat asked me to review a couple of things. First of all, how many of you have already downloaded AstroImageJ? Okay, good. Does anybody have any issues with downloading it? The reason I say it is because if you go on AstroImageJ, there's the release notes that kind of look a little scary as far as the different Windows installation things to do, etc. And let me just kind of quickly review that. Part of it has to do with whether you have Java already installed or not, whether you have a 32-bit or 64-bit machine. So I think generally most of us probably have Java installed, I would think by now, with all the applications that are out there. So the file that's labeled AstroImageJ, in this case when I printed it out, 3.00 blah 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 underscore windows.zip with no Java would be if you already have Java installed on either a 32 or 64-bit system. There's variations of it if you don't have Java installed for a 64 or 32-bit. So depending upon whether you have Java installed or not, there's different zip files you would download. So you just download it, unzip it, install it. It's pretty easy and it should come up. So if anybody has any problems doing it, let me know. We'll try to resolve it.
Do you recommend it with Java?
It depends if you have Java installed or not.
Download Java first if you go?
Why don't you, I don't think it'd be harmful to, maybe somebody else here can answer it, if you go ahead and install it with the option as if you didn't have Java, see what happens. I don't think it's going to do anything harmful. Okay. So the other thing, I think many of you know by now that on my website there's this guide. What this does is it goes through best practices and step-by-step through Astro ImageJ, doing a complete exoplanet transit. And that's kind of where we are. So let me jump to this addendum I handed out. And talk about a few things here. So this now is all related to Astro ImageJ. And what I wanted to do is to go through some of the terminology that Astro ImageJ uses. What do I do with my pointer? The first is the target stars are referred to as the letter T, capital T. And generally, there's one target star, so you'll see T1. The comparison stars begin with the number 2, so C2, C3, C4, so on. They don't start with 1. That's not so it's not confused with T1 up there, I suppose. What Astro ImageJ will produce, which is the whole key, is a thing called a measurements table. Think of it like an Excel spreadsheet. It's actually either a text or a spreadsheet. But it has in it columns representing the different measurements. The key measurement is source minus sky, which is what we talked about here. This is the ADU counts in that aperture for the star after the sky background has been taken out. So source dash sky, or source minus sky, C2, are the ADU counts of ComStar C2 after the sky background is taken out. That's the measure that is used to total up all the ComStar counts, for example, here. It's also the measure, if this were source minus sky T1, it would be the count of all of the ADU counts for the target. So source minus sky, think of it as the net ADU counts for a star, either target or comparison star. Total C counts is this number here. The total counts of all of the net ADU counts after the sky has been taken out. Relative flux is the source minus sky for the target, which is, again, the counts after sky over the total C counts. Now, we also do relative flux for each comparison star. And the way that's done is, again, the source minus sky for the comparison star over the total counts of all the comparison stars except this star. So it's comparing a comparison star to all the other comparison stars. Not the target at all, but just all the... So that's what we use to see if there's any light curve variation for a comparison star. So this is the key for the target. This is the key for the comparison. Yes?
The denominator there isn't normalized in any way. It just sum up all the counts from all the comparison stars.
Right.
Why don't they normalize?
So the question is it normalized at all? It's just the total counts. There is, after this, a normalization for plotting purposes that does take place, but for here, it's just that ratio. Yeah, in the table, that's what it is. For plotting, it's actually shown as a normalized value. Yeah.
Can I answer that?
Yes.
I think the reason why you use the total counts for the stars is that it's naturally weighting the brighter calibration stars slightly more than the fainter ones. So it's the appropriate thing to do is to just add up all the counts.
Yeah.
You're effectively weighting them by their brightness
Yeah.
that way as well.
But I think maybe we're talking about a different kind of normalization would be after this is done, all of this is normalized to 1. So it's relative to 1, namely, so you get sort of a percentage. I think is maybe what you're talking about. Yeah. Okay. Any questions about that? How How are we doing with those thumb drives? Everybody still working on them? Okay. All right. Okay. All right. Okay. So I know we're going to go through this in detail tomorrow, and I don't expect you to remember much of this, but just to get a general flavor of the pipeline of what we're going to go through. So we're going to take all of our calibration files. We're going to take our raw science images, and there's a module in ImageJ called DP, CCD Data Processing Function. What that does is it takes all of these raw files, so there might be 17 biases, 17 dark, 17 flats, creates a master for each of them. That's the first thing it does. Then it calibrates the science images with respect to those masters, and optionally add some of the FITS fields, like BJD, TDB. So in one step, it will do the calibration, and it will do the update of the FITS fields. What comes out of that is a set of files called pipeline out files. You can actually name it whatever you want, but that's sort of the default, so I'm calling it here. So out of this now, you've got calibrated files all ready to go for processing. So the next thing then that happens in the pipeline is these pipeline files go, you bring them up on your screen. There could be 100 of them, could be 1,000 of them, whatever. But on one of the images, generally the first image, you determine what the full width half maximum is. And remember what I said this morning, is theoretically every star in that image should have the same full width half maximum, because it's independent of the brightness of the star. It's just a function of the size of that airy disk, which is just a function of wavelength and focal length. So you determine what that is, and there's an easy way to do that with a alt left click thing on your computer when you've got an image up. Astro ImageJ will bring up a screen showing you what that is, and will give you recommendations for the aperture and annulus radii. So you don't have to do any computation. It'll just do that automatically, which is really great because, and it follows a rule of thumb that the, just for what it's worth, the number of pixels in the annulus, in the donut, should be 4 times the number of pixels in the aperture. That's sort of a rule of thumb. Yes?
So if you don't have autofocus running and occasionally refocusing, the thing's going to go, this point spread function is going to get a little bigger as time goes on. So in that case, how do you choose the annulus?
Yeah, the question is, if you don't have autofocus on and your focus changes during the observation session, and therefore you selected an aperture and annulus based on certain assumptions, that could be a problem. So autofocusing, honestly, I have not, maybe it's the conditions I'm in, I have not seen that as a problem over a 4 or 5 hour period, any need to autofocus. And it may be because of my setup or whatever, so I've not had that problem. I'll consistently keep, depending upon seeing conditions, not much change across the 4 or 5 hours. Now, maybe things are different here, and maybe you have to worry about it, but that would be a concern. And that's why, if you do have autofocus capability based on temperature compensation changes, then do it. Yes?
In pre-processing the images, if you have vignetting, do you need to crop that out?
So the question is, if you have vignetting, do you need to crop it out? If your comp stars and your target are in your center field of view, and it's not, you think not being affected by vignetting, then not to worry about it, but it depends on how bad it is. I don't know. Now, another issue that may occur, especially if there's a problem with your polar alignment, is if the star starts drifting. And then what's going to happen is when you place these apertures and annulus on the star, all of a sudden the star is drifting and is drifting out of that aperture and annulus. That's a function of the fact you're not the auto guiding isn't good, or you're not polar aligned and you're doing deck drifting. If that's the case, there is a way for Astro ImageJ to align all your images. And what you do is, and we can go through it tomorrow, you'll put an aperture on a couple of stars, and it'll go through. It's as if it's, those of you who do deep sky stuff, it's as if you're registering the images. It'll kind of put them aligned with each other, and it'll create a new directory called aligned with your aligned images. That's what you would then go back to and continue with your analysis. So there is that little quirk that will happen. The other thing, of course, is if it's a meridian flip. If it's a meridian flip, all of a sudden your apertures and annulus are going to be on nothing because your stars have flipped to the other side. So, and the example I have here was in a meridian flip, and we'll see that tomorrow. So what I'll do is I'll break up the differential photometry into two phases, pre-flip and post-flip. So I'll do a pre-flip analysis. It'll create so many rows in the measurement table. I'll do the post-flip analysis, and it'll create the rest. So that way it'll be a continuous one measurement table that includes pre-flip and post-flip. Yes?
On the alignment, are you doing an interpolation between pixels, or is it perhaps a bit more rigorously just looking at where the centroid is and then moving the apertures to the stars?
The alignment...
Moving the images to the apertures, or moving the apertures to the stars, I guess.
Well, what the alignment does is you pick, let's say, two stars, and it puts it on the centroid of the stars. And then what it's doing is just trying to match probably that alignment. I'm not sure. I'm sure it's still looking at the centroids of the stars on the next images.
So it's moving the aperture to follow the stars?
No, it's moving. It'll move the image to line the images up, so they're all sort of stacked on top of each other or lined on.
My concern and question is there interpolation involved in doing
No.
that? Because if you're going to move everything over by 0.45 pixels, you know, it's
No. It's still. How can I put it? What will happen is the star, the background of the star is going to move with it.
yeah.
And so if it moved on to a dust mode, it's going to be on a dust mode
Yeah.
when it's moved. That's not going to have changed. Yeah. Okay. The other thing I do is I'll just quickly sequence through all the images, just play it through, and just note what images are bad. By bad, we mean, cosmic ray hits through the target star, airplanes going over, meteors cutting through it, crazy stuff like that, glitches and guiding or something. And what I'll do is I'll eliminate those images. I'll move them to a separate folder I call quarantine, just to get them out of there, and then continue on. So there's a little step here in case, just to get those out of the way. And then once everything's aligned and everything, I'll select the appropriate comp stars and start doing the analysis. So the next step is doing the multi-aperture photometry, as we talked about. These radii are already defined out of Astro ImageJ. We put in these factors that affect the uncertainty regarding our CCD camera. We put in limits on linearity and saturation. What these are for is Astro ImageJ, as it's doing its processing, if it sees that the ADU counts in any of the target or comp stars have exceeded what we put here, it will flag it, if you will. So you will know at the end of this if you had done any saturated, if any of the images were saturated with the comp stars or target stars. Place the apertures on it, and when photometry is completed, the measurement table is created. Again, this is the key to Astro. This is what everything else revolves around, this measurement table. Which again, think of it like a spreadsheet. It has the time, it has RA and DEC, it has the relative fluxes, it has errors, it has signal to noise ratio, everything else. The other cool thing it has is it has the coordinates of the target star and the comp star on the image. So what you can use that for, as I've done before, is to see how much you varied through your observation. You can see, that's why I say I'm confident in some cases I can do 1 or 2 pixels, because I look at that column and I can see how much that has varied as far as the XY coordinates of a star. The next one is now where we've got the measurements table. We select, you can select different time bases. BJD, TDB is what we use. We fill in some titles and subtitles, and we then define the left and right values for where we think the predicted ingress and egress times are. I'll cover some of this more detail tomorrow. It'll automatically do a range on the x-axis and the y-axis, and if a meridian flip occurred, we can designate where that meridian flip took place. And the reason is because when a meridian flip occurs, of course, your target and comp stars are going to go on a whole other part of the CCD detector. They're probably going to change arbitrarily in magnitude. And so to correct for that, what AstroImage-J does is if you designate where the meridian flip took place, it will adjust that curve downward, let's say, to compensate for that arbitrary change, because it knows historically where you were, and it'll assume, therefore, that that jump occurred because of that meridian flip. So that's a really nice feature for those of us with German equatorial mounts. And then there's a screen called Dataset 2 Fit Screen. This will all make sense tomorrow, where you put in what we call priors, namely the predicted period, R star, the predicted inclination, limb darkening coefficients. Now on some of these you can lock them to say, you know, when you do the model, force it to these values. In some cases you unlock it. The 2 ones to lock are these values. Everything else should float and let AstroImage-J figure out what they are. So just like with any modeling, you can set some input parameters and let the model calculate for you what you want, or you can force some input parameters. So the idea is to just force these 2 limb darkening coefficients, let AstroImage-J figure out all the rest. This then screen allows us to plot all the different plots you saw earlier. I'm not going to go through these in detail here, but the first thing, as I said, is to plot air mass to see how close we are to that. Then plot the source minus sky counts for the comparison stars and the target star to see if there's a lot of scatter, in which case we may need to get rid of some comparison stars. And then to do the last one, which is the relative flux of the target star. And finally, this screen allows us to play around with different D-trend parameters, and again, I'll go through it tomorrow, to get the to optimize the model. And then we're done. And now we've got a light curve that, with the best model fit to our data, the output of that are the key parameters, such as radius of the star, the size of the orbit, and the inclination. Okay, here's a drive if anybody is interested in loading up. Going once. Okay. Yep. And we got another. Anybody else? Rachel? Oh, you're done. Okay. Going once? Okay. Okay. Well, that sort of, I think, does it for today. Before I wrap up, let me just see if there's any questions anybody has. Yes?
Hi, on the USB, do you have the calibrated images as well, or is it just the...
On the drive? No, that's an exercise for the students. We're going to do that tomorrow. Yeah. We're going to do the calibration tomorrow. I mean, I do have, we say calibrate, I do have the raw bias darks and flats, but I haven't calibrated. I haven't created the darks. I'm sorry, I haven't created the masters for those, and I haven't calibrated. We're going to do that tomorrow. I mean, I've done it myself, but not here. Yes.
When matching optics to cameras, is there a optimum arc second per pixel? Makes sense for computers?
Well, the general rule of thumb is to look at your full width half maximum and see that it, it's consistent with what your seeing conditions are. So depends on your seeing conditions. You don't want to undersample or oversample. So it's your image scale is a function of what your full width half maximum is. I know for me, my image scale is 0.45 arc seconds, but my seeing is 2 arc seconds. So I'm sampling more than I probably need to. And sometimes I'll bin, necessary. But generally the rule of thumb is to get your image scale close to your full width half maximum, so you're not wasting any, CCD detector photo sites or whatever. So, it's the same thing with deep sky imaging. I think this general rule of thumb is the same.
So you have been,
I have binned for exoplanets. In fact, my normal binning actually is 2x2. That's what I'm doing here. Yeah, because it's sufficiently small enough, and binning at 2x2 reduces the image sizes.
So you could actually shoot with a refractor
Yeah. Oh yeah.
if you bend.
Yeah. One of the things, by the way, I didn't mention that there have been a couple of cases I've actually been curious to get the results of people using a DSLR camera for doing this stuff, and I'd love to try to see what the results of that are.
You could extract just one of the color bands, like green.
Well, or if they bin, it'll turn into a monochrome camera, but the resolution is less. So I'm not sure what they've done. I have heard of some folks who have done that. Okay, any other questions? Okay, Pat, what time are we reconvening tomorrow?